calculate voltage drop on a 480Y/277 volts multiwire branch circuit, use the 480 volts for the voltage drop calculation. Even though the lighting is connected line to neutral at 277 volts, the circuit remains a 480Y/277 volts multiwire branch circuit. The voltage drop is calculated based on the line-to-line voltage, which is 480 volts in this case. The voltage drop formula is voltage drop equals current times distance divided by voltage times conductor size. Using the line-to-line voltage ensures that the voltage drop calculation is accurate and that the circuit is protected properly. Here's a more detailed explanation of why using the line-to-line voltage is crucial for accurate voltage drop calculations in a multiwire branch circuit. Firstly, let's define what a multiwire branch circuit is. A multiwire branch circuit, or MWBC, is a circuit that has two or more grounded conductors with a voltage between them and a grounded conductor having equal voltage between it and each ungrounded conductor of the circuit, which is connected to the neutral or grounded conductor of the system. Multiwire branch circuits are commonly used to provide multiple 120 volts or 277 volts circuits from a single three-phase or split-phase panel. In a 480Y/277 volt system, the voltage between any two-phase conductors, that is line-to-line, is 480 volts, and the voltage between any phase conductor and the neutral conductor, that is line-to-neutral, is 277 volts. The 480Y/277 volts configuration is a three-phase, four-wire system where the Y indicates the configuration of the transformer windings. The 480 volts is the line-to-line voltage, and the 277 volts is the line-to-neutral voltage. Understanding the voltage relationships in this system is critical for calculating voltage drop accurately. The primary reason to use the line-to-line voltage for voltage drop calculations in a multiwire branch circuit is to ensure that the calculation reflects the overall circuit behavior. While the loads, in the example lighting, are connected line to neutral at 277 volts, the circuit is part of a larger 480 volts system. The voltage drop occurs along the entire length of the conductors, and this voltage drop is influenced by the total voltage potential in the circuit, which is 480 volts between the lines. The line-to-line voltage represents the maximum potential difference in the circuit. When current flows through the conductors, the voltage drops proportionally along the length of the wire. Using the line-to-line voltage accounts for the total potential voltage, thus providing a more accurate representation of the voltage drop. If you were to use only the 277 volts line-to-neutral voltage, you would underestimate the voltage drop because you would not be accounting for the entire voltage potential within the circuit. Overlooking the 480 volts potential could lead to selecting conductors that are too small, resulting in excessive voltage drop and potential overheating of the conductors. Accurate voltage drop calculations are essential for several reasons. Firstly, maintaining proper voltage levels at the load is crucial for the proper operation of electrical equipment. Most electrical equipment is designed to operate within a specific voltage range, typically plus or minus 5% to 10% of the rated voltage. Excessive voltage drop can cause equipment to malfunction, operate inefficiently, or even fail prematurely. For example, lighting may dim, motors may overheat, and electronic devices may not function correctly. Secondly, excessive voltage drop can lead to increased energy consumption and higher operating costs. When the voltage at the load is lower than the rated voltage, the equipment must draw more current to perform the same amount of work. This increased current results in higher power losses in the conductors, which translates into wasted energy and increased electricity bills. Thirdly, voltage drop calculations are important for ensuring compliance with electrical codes and standards, such as the National Electrical Code, or NEC. The NEC specifies the maximum allowable voltage drop for branch circuits and feeders to ensure the safe and efficient operation of electrical systems. For example, the NEC recommends that the voltage drop on branch circuits should not exceed 3% and the voltage drop on feeders should not exceed 5% for a total voltage drop of no more than 5% to the farthest point of utilization. The voltage drop formula is voltage drop equals current times distance divided by voltage times conductor size, where voltage drop is the voltage drop in volts, current is the current flowing through the conductor in amps, distance is the length of the conductor in feet, voltage is the voltage of the circuit in volts, and conductor size is a factor related to the conductor material and size, often derived from tables. To illustrate how to use the line-to-line voltage in the voltage drop calculation, consider a practical example. Suppose a 480Y/277 volts multiwire branch circuit is supplying 3000 watts of lighting on each leg. The circuit is 200 feet long, and the conductors are number 12 American wire gauge copper wires. Step 1 is to calculate the current in each leg. The current can be calculated using the formula current equals power divided by voltage. In this case, the power is 3000 watts and the voltage is 277 volts. Therefore, the current is 3000 watts divided by 277 volts, which equals approximately 10.83 amps. Step 2 is to determine the appropriate conductor size. Number 12 American wire gauge copper wire is commonly used for 20 amp circuits, which is suitable for this application since the calculated current is 10.83 amps. Step 3 is to use the voltage drop formula to calculate the voltage drop. The voltage drop formula is voltage drop equals current times distance divided by voltage times conductor size. We will use the 480 volts line-to-line voltage in the calculation. The voltage drop constant K for copper is approximately 12.9 ohms circular mils per foot. For number 12 American wire gauge copper wire, the circular mils area is 6,530 circular mils. Substituting these values into the formula, the voltage drop is 2 times 10.83 amps times 200 feet times 12.9 ohms circular mils per foot divided by 6,530 circular mils divided by 480 volts. The voltage drop equals approximately 0.18 volts. Note that the factor of 2 is used because we are considering the voltage drop for a 2-wire circuit, line and neutral. To calculate the percentage voltage drop, divide the voltage drop by the circuit voltage and multiply by 100. Percentage voltage drop equals voltage drop divided by voltage times 100. In this case, the percentage voltage drop is 0.18 volts divided by 480 volts times 100, which equals approximately 0.4%. This voltage drop is well within the recommended limit of 3% for branch circuits. Now let's consider what would happen if we incorrectly use the 277 volts line to neutral voltage in the voltage drop calculation. Using the same formula, but substituting 277 volts for the voltage drop becomes 2 times 10.83 amps times 200 feet times 12.9 ohms circular mils per foot divided by 6,530 circular mils divided by 277 volts. The voltage drop equals approximately 0.31 volts. The percentage voltage drop is 0.31 volts divided by 277 volts times 100, which equals approximately 0.11%. While this value still appears to be within the recommended limit, it is significantly lower than the actual voltage drop calculated using the 480 volts line-to-line voltage. This discrepancy highlights the importance of using the correct voltage value to ensure accurate voltage drop calculations. Using the 277 volts instead of the 480 volts would lead to an underestimation of the voltage drop, potentially resulting in the selection of undersized conductors and a higher actual voltage drop than anticipated. This could lead to operational issues, increased energy consumption, and potential safety hazards. Understanding the implications of voltage drop is also important for making informed decisions about conductor sizing and circuit design. The NEC provides guidelines for allowable voltage drop, and these guidelines should be followed to ensure the safe and efficient operation of electrical systems. In addition to using the correct voltage value, other factors could affect voltage drop calculations. Firstly, conductor material plays a significant role. Copper conductors have a lower resistance than aluminum conductors, resulting in lower voltage drop for the same conductor size. Secondly, conductor temperature affects resistance. As the temperature of a conductor increases, its resistance also increases, leading to higher voltage drop. The NEC provides tables that adjust conductor ampacity based on temperature to account for this effect. Thirdly, the presence of harmonics in the electrical system can also affect voltage drop. Harmonics are non-sinusoidal waveforms that can increase the root mean square, or RMS, current in the conductors, leading to higher voltage drop. In summary, when calculating voltage drop on a 480Y/277 volts multiwire branch circuit, always use the 480 volts line-to-line voltage to ensure accurate calculations. This approach accounts for the total voltage potential in the circuit and helps prevent underestimation of the voltage drop. Accurate voltage drop calculations are essential for maintaining proper voltage levels at the load, minimizing energy consumption, and ensuring compliance with electrical codes and standards. By following these guidelines, you can design and install electrical systems that are safe, efficient, and reliable. For additional clarification, let's reiterate the key points. 1. Always use the line-to-line voltage for voltage drop calculations in multi-wire branch circuits. 2. Understand the voltage relationships in a 480Y/277 volt system. 3. Accurately calculate the current in each leg of the circuit. 4. Select the appropriate conductor size based on the calculated current and allowable voltage drop. 5. Use the voltage drop formula to calculate the voltage drop. 6. Consider the impact of conductor material, temperature, and harmonics on voltage drop. 7. Comply with the NEC guidelines for allowable voltage drop. Understanding these principles and applying them correctly will ensure the proper operation and longevity of electrical systems. Proper voltage drop calculation is not just about theoretical accuracy, it has real-world implications for the performance and safety of electrical installations. Ignoring these principles can lead to a variety of problems. Firstly, reduced equipment lifespan. Electronic devices and motors are particularly sensitive to voltage fluctuations. Operating equipment outside of its specified voltage range can significantly shorten its lifespan, leading to premature failure and costly replacements. Secondly, inefficient operation. When voltage drops too low, equipment must work harder to achieve the same output. This increased effort translates directly into higher energy consumption and increased operating costs. Thirdly, safety hazards. Excessive voltage drop can cause conductors to overheat, increasing the risk of insulation breakdown and electrical fires. In severe cases, it can also lead to equipment malfunction and potential safety hazards for personnel. To further emphasize the importance of accurate voltage drop calculations, consider the perspective of an electrical inspector. During an inspection, one of the key areas of focus is voltage drop. Inspectors will often use voltage drop calculators or perform manual calculations to verify that the voltage drop is within acceptable limits. If the voltage drop exceeds the allowable limits, the installation may fail inspection, requiring costly rework and delays. Furthermore, inaccurate voltage drop calculations can lead to legal and financial liabilities in the event of an electrical incident. If a fire or equipment failure is attributed to excessive voltage drop, the responsible party, whether it is the designer, installer, or owner, may be held liable for damages and injuries. Therefore, it is essential to prioritize accurate voltage drop calculations and to ensure that all electrical installations comply with the applicable codes and standards. In conclusion, the practice of using the 480 volts line-to-line voltage for voltage drop calculations in 480Y/277 volts multiwire branch circuits is not just a theoretical exercise, it is a fundamental principle of electrical engineering that has significant implications for the performance, safety, and reliability of electrical systems. By understanding and applying this principle, you can ensure that your electrical installations are safe, efficient, and compliant with the applicable codes and standards. Furthermore, Always refer to the latest edition of the NEC and consult with qualified electrical professionals for specific guidance on voltage drop calculations and electrical system design.